When you hop into your car, maybe just for a quick grocery run or maybe a long road trip, you probably don't spend much time thinking about the intricate web of engineering that actually makes that journey safe.
No, you really don't.
Yeah,
You just expect it to work.
exactly. We often take it for granted. The brakes just work, the airbags deploy if, God forbid, they're needed, the power steering responds instantly.
Mm.
But beneath that sleek exterior, beyond the comfy seats and the cool tech, there's this incredibly rigorous world of engineering. It's all built on these meticulous standards designed purely to keep us and everyone else on the road safe.
Absolutely. It's a level of scrutiny that I think would genuinely surprise most people.
Mhm.
Every component, every single line of code is analyzed, verified. It's intense.
It really is. So today, we're going to peel back a layer of that meticulous design. We're going to dive deep into one of the absolute cornerstones of automotive functional safety, ISO 26262.2018.
Ah, the big one.
The big one indeed, specifically Part 9. Now, this part zeroes in on what they call Automotive Safety Integrity Level, ASIL-oriented and safety-oriented analyses.
Sounds like a mouthful, doesn't it?
It does. But trust me, this is where the rubber truly meets the road in ensuring your vehicle isn't just fast or smart, but fundamentally undeniably safe.
That's exactly right. If you think of functional safety as like the big promise that a vehicle's electronic systems will operate correctly and, crucially, not cause unreasonable harm,
Right.
then ISO 26262-9 is basically the playbook. It's the how-to for systematically proving that promise. It gets into the concrete analytical methods engineers use all the way through development.
So it's not just hoping it's safe, it's proving it.
Precisely. It's
Yeah.
about being incredibly proactive, systematically finding potential hazards before they happen, and then building in all the necessary safeguards right from the start and verifying them at every single step.
Absolutely. So our mission today is to unpack how ASILs, these fundamental safety integrity levels, really drive the rigor in development, and then how these various powerful safety analysis methods get applied throughout a vehicle's life cycle. We're talking everything from the initial idea, the concept, all the way through production, operation, even decommissioning.
The whole lifespan.
The whole thing, yeah, all to make sure everything functions safely. So consider this your shortcut, if you will, to truly understanding this critical yet often invisible area of automotive engineering.
By the end, you'll have a much deeper appreciation for that invisible safety net.
Exactly. You'll see the engineering, even if it's hidden. Okay, let's start with what really feels like the central nervous system of this whole safety philosophy, ASIL.
ASIL.
For those perhaps less familiar, we're talking about the Automotive Safety Integrity Level. It honestly feels like the North Star,
Yeah.
the fundamental guiding principle in functional safety. So maybe you can start us off. What exactly is ASIL, and why is it so absolutely central to everything?
Right. Well, what's really fascinating here and important to grasp is that ASIL isn't just some classification label you slap on a part or a function. It's much, much deeper than that.
Okay.
At its core, ASIL is a crucial attribute, and it's derived directly from a really comprehensive hazard analysis and risk assessment, HARA, as it's often called. That whole process is rigorously defined earlier in the ISO 26262 standard in Part 3.
So it comes from analyzing potential dangers first.
Exactly. Imagine a scenario where a system failure could potentially lead to harm. Let's say the brakes failing completely. The ASIL is essentially a measure of how bad that potential harm could be.
Severity.
Right, severity. But it's coupled with the probability of actually being in that hazardous situation.
Exposure.
Yeah, and also how well the driver could potentially react to control the situation if the failure happened.
Controllability. So S, E, and C.
Exactly. Those three factors, severity, exposure, and controllability, determine the ASIL. And its fundamental role, its whole purpose really, is to dictate which specific requirements and recommendations from the standard are applicable.
Applicable to what exactly?
Applicable to avoiding what the standard calls unreasonable residual risk. And this applies throughout the entire functional safety life cycle.
Ah, so it's not just about the design phase.
Not at all. It's a living attribute.
Yeah.
It influences how the system is developed, how it's produced, how it's operated, how it's serviced, and even eventually how it's decommissioned. It touches everything.
Wow.
And to put it simply, there's a direct sort of proportional relationship here.
Okay.
The higher the ASIL, the more stringent the requirements become,
Yeah.
and the more rigorous all the development and validation activities have to be.
Makes sense. Higher risk, more care needed.
Precisely. The ASILs range from ASIL-A, which is the least demanding level of safety integrity, all the way up to ASIL-D. And ASIL D represents the most stringent, the highest level of required rigor.
So D is the most critical.
Absolutely.
Yeah.
So if you have a safety goal that's classified as ASIL D, maybe something like preventing unintended acceleration, where a failure could lead to severe injury or death, and it's highly probable or very difficult for the driver to control.
Right. A worst case scenario.
A very serious scenario. Then every activity, every process, every verification step, from the earliest design thoughts to the final validation testing, must adhere to the absolute highest level of strictness that's outlined in the standard.
And that applies across the board.
Across the board. Initial concept, detailed hardware design, software development, tons of testing, verification, validation, even how the vehicle gets serviced later on. ASIL D demands the maximum diligence everywhere.
So it's almost like a detailed design brief where the safety requirement doesn't just tell you what you need to achieve for safety, but it comes stamped with its own inherent risk level tag, right? And that tag dictates exactly how carefully every single step in the process needs to be executed and, crucially, how thoroughly it has to be verified.
That's a great way to put it. It's not just a target to aim for. It's a constant reminder of the potential gravity of failure and the level of diligence needed to prevent it.
It keeps the stakes front and center.
Precisely. And this rigor, this demand for diligence, it propagates, it flows down through the entire development chain.
How so?
Well, the ASILs is initially assigned as an attribute of the top-level safety goal.
Yeah.
Let's stick with prevent unintended acceleration. Let's say that's determined to be ASIL D.
Okay.
That ASIL D attribute is then inherited by every subsequent safety requirement that's derived and refined as you go deeper into the design phases.
So it cascades down.
It cascades down. That means every functional safety requirement supporting that goal, every technical safety requirement derived from those, and eventually every individual hardware and software requirement that contributes to preventing that unintended acceleration. They all inherit that ASIL D attribute.
I see. So the rigor doesn't get diluted as you get more specific.
Exactly. It ensures that the appropriate level of rigor is maintained consistently, all the way from the highest level safety objective down to the most granular individual hardware components and software modules. It's absolutely fundamental for maintaining traceability and ensuring safety measures are applied consistently everywhere they need to be.
That makes perfect sense. It's a cascading effect of rigor, ensuring nothing falls through the cracks. But, okay, given this inherent demand, especially with something like an ASIL D requirement, which sounds incredibly demanding and probably pretty expensive to implement across every single element of a complex system.
It can be, yes.
Are there any, smart strategies, ways to manage or maybe tailor these ASIL requirements to optimize development, but without compromising that absolute foundational safety? It seems like a huge engineering challenge.
That is a very perceptive question. And yes, absolutely. The standard anticipates this. It brings us to a really powerful concept called ASIL decomposition.
ASIL decomposition.
It's a core part of how engineers intelligently manage functional safety complexity.
Okay, let's unpack this then. ASIL decomposition. Because, an ASIL D requirement just sounds incredibly demanding. Are engineers simply stuck with applying that highest level of rigor across an entire complex system? Or is there, like you said, a way to intelligently manage that complexity without, cutting corners on safety?
That's precisely where ASIL decomposition comes into play. It's described in the standard as a powerful ASIL tailoring method. And the sort of profound insight here is that achieving functional safety isn't always about making one single component impossibly perfect, impossibly robust.
Right, that might not even be feasible sometimes.
Exactly. Instead, it's often about cleverly distributing the safety responsibilities across multiple, truly independent parts. So the primary objective of ASIL decomposition is to systematically break down a single high ASIL safety requirement. Let's stick with our ASIL D example. Into multiple redundant safety requirements. These new decomposed requirements are then allocated to different design elements, different hardware components, different software functions that are, and this is the absolute key phrase, sufficiently independent from each other.
Sufficiently independent. We'll need to dig into that phrase later, I bet.
Oh, absolutely. But think of it like this. Instead of relying on one single, incredibly strong and likely very expensive pillar to hold up a heavy roof, you distribute the load across multiple strong pillars. If one pillar has an issue, the others can still support the roof.
Redundancy through distribution.
Precisely. And the practical benefits are pretty significant. This approach offers the opportunity under strict conditions, mind you, to assign a potentially lower ASIL to some of these decomposed safety requirements.
Lowering the ASIL, how does that help?
Well, if an element only needs to meet, say, ASIL-B requirements instead of ASIL-D, it can dramatically reduce the complexity of designing and verifying that specific element, and consequently can reduce the development cost and time for that element.
Okay, so potentially faster and cheaper for that specific part.
For that part, yes.
Mhm.
But, and this is crucial, it's done without compromising the overall safety objective of the original higher ASIL requirement. You're achieving the same high level of safety, but through a distributed, fault-tolerant architecture where the system remains safe even if one of these pillars should happen to fail.
It sounds a bit like, okay, instead of building one massive impenetrable bank vault for all your valuables, you build, say, 2 or maybe even 3 slightly less impenetrable vaults. But crucially, you make them completely separate, completely independent, and ensure that if one vault gets breached, the others are unaffected and still protect the contents.
That's a brilliant analogy.
Yeah.
That captures the essence perfectly. The overall security, the overall safety remains the same or potentially even higher because of that redundancy and independence.
Clever. But it sounds like there have to be some serious rules around this. You can't just arbitrarily lower ASILs, right?
Absolutely not. And this is critical. ASIL decomposition is not a loophole. It's not a shortcut to making things less safe.
Yeah.
It's a carefully managed strategy built on very, very strict principles.
Okay, what are the main principles?
The standard emphasizes one core principle above all.
Yeah.
Each decomposed safety requirement must be capable of complying with the initial higher-level safety requirement all by itself.
By itself? Meaning?
Meaning, if you decompose an ASIL-D requirement into, say, 2 ASIL-B-D requirements allocated to 2 independent elements, each of those elements implementing its ASIL-B-D requirement must be capable on its own of achieving the original ASIL-D safety goal if the other element fails.
Ah, so the redundancy has to be truly effective. Each part needs to be able to carry the load alone, if necessary.
Exactly. That inherent redundancy and independent capability is what makes the decomposition valid and effective. It's about having multiple independent safes, as in your analogy, each fully capable of protecting the valuables on its own.
Got it. And what about that sufficiently independent part? That sounds like a big hurdle.
It is, and it's the absolute crucial precondition for ASIL decomposition. The architectural elements that implement these decomposed requirements must be demonstrably, provably, sufficiently independent.
How do you prove that?
This isn't just a casual claim or an assumption. It requires rigorous proof. If that sufficient independence cannot be rigorously proven through detailed analysis,
Then what?
then the decomposition isn't allowed. The decomposed requirements and the architectural elements they're allocated to must inherit the original higher ASIL. So if you can't prove independence for your ASIL decomposition, everything stays ASIL-D.
Correct. And this is precisely where the exhaustive analysis of dependent failures, the DFA we mentioned, becomes absolutely critical. That analysis, which we'll dive into shortly, is specifically designed to ensure there's no plausible common cause failure or cascading failure that could undermine the intended independence and violate the initial safety requirement.
Okay, so DFA is the gatekeeper for decomposition. In many ways, yes. The standard is crystal clear. Evidence of this independence must always be documented and made available. You can't just claim it. You have to show your work. And simply duplicating the exact same component, what's called homogeneous redundancy, generally isn't enough to justify reducing the ASIL without that rigorous dependent failure analysis to prove deep independence, especially against shared systematic flaws.
Wow. Okay, so the ASIL number might change for individual elements after decomposition, but the ultimate safety obligation, the system's overall ability to achieve that safety goal, does not change one bit.
Precisely. It's truly about distributing the safety burden across independent capable elements and then putting in the hard work to prove that independence with a whole other layer of detailed analysis. It definitely requires significant upfront engineering effort to justify doing it.
It's not the easy way out, then.
Not at all. It's the smart way, potentially, but requires meticulous execution. And the standard actually provides specific permitted decomposition schemas. It lays out exactly how an ASIL is allowed to be tailored.
Okay, like formulas.
Sort of, yeah. For instance, for an ASIL-D requirement, you have a few specific structured options. It can be decomposed into one ASIL-CD requirement plus one ASIL-ED requirement.
C and A making D.
Essentially, yes, in terms of the combined rigor and independence.
Mm-hmm.
Or another option is one ASIL-BD requirement plus another ASIL-BD requirement.
2 B's making a D.
Okay, and a really common one you see in practice involves an ASIL-ED requirement plus one QMD requirement.
QM, looks it.
QM stands for quality management. It basically means that for that specific element assigned QM, standard automotive quality management processes like IATF 16949 are considered sufficient because there's a separate, fully independent safety mechanism developed to the higher ASIL, the DD part, specifically designed to detect and control failures of that QM element.
So the QM part does its job, but if it messes up, the ASIL-DD part catches it.
That's the idea. The safety mechanism covers the potential failures of the intended functionality.
Okay. Are there similar schemas for lower ASILs?
Yes. For an ASIL-C requirement, the allowed decompositions are 1 ASIL-BC plus ASIL-AC, or 1 ASIL-CC plus QMC.
Right.
For an ASIL-B requirement, it's 1 ASIL-AB plus ASIL-AB, or 1 ASIL-BB plus QMB.
A plus A makes B. Okay.
And even for an ASIL-AA requirement, which is the lowest safety level, if you need to decompose it for some reason, the only option is 1 ASIL-AA plus QMA.
So these schemas provide a very clear, predefined framework for how decomposition is allowed.
Exactly. It standardizes the approach.
Now, I noticed the notation there like ASIL-CD, the ASIL in parentheses. That seems important.
Oh, it's super important. That notation, the ASIL in parentheses like ASIL-CD, tells you the ASIL of the original safety requirement before decomposition.
So it tracks the lineage.
Precisely. It ensures that even if the immediate requirement allocated to an element is, say, ASIL-C, everyone knows it originated from an ASIL-D goal. It maintains traceability back to the initial risk assessment and ensures the original design rigor isn't forgotten. It's like a genetic marker, as you said earlier, ensuring you remember its origin and the context.
That's clever. Keeps the original intent visible.
It does. And the standard provides a really important cautionary example to highlight that effectiveness is paramount. It explicitly states that a simple watchdog timer alone cannot sufficiently cover all the potential failure modes of a complex microprocessor.
Even if you try to decompose.
Even if you try to decompose an ASIL-D requirement by assigning, say, QM to the microprocessor itself and ASIL-D to the watchdog. The watchdog might catch some things, like the processor freezing, but it won't catch subtle calculation errors or incorrect outputs.
So the safety mechanism has to be truly comprehensive.
Exactly. The effectiveness and the coverage of the safety mechanism are absolutely paramount. It's not just about splitting ASIL numbers on paper. It's about ensuring the functionality of the safety measure genuinely covers the full scope of the risk and the potential failure modes of the element it's monitoring or backing up.
Right, the physics and logic have to work.
Absolutely. And furthermore, even when you use decomposition, the requirements for evaluating hardware architectural metrics remain unchanged.
What metrics are those?
These are things like the single point fault metric, SPFM, and the latent fault metric, LFM. They measure how well the hardware architecture handles random hardware failures, how effectively safety mechanisms detect or control single faults, and how well they prevent hidden, latent faults from causing problems later.
So decomposition doesn't let you off the hook for hardware reliability targets.
Not at all. Those fundamental hardware reliability targets defined in ISO 26262-Part 5 still apply based on the original ASIL. Decomposition doesn't lower the bar there.
Okay.
And critically, all the integration activities, all the verification activities, and all the confirmation measures like reviews and audits that you perform after decomposition must still be applied in accordance with the original ASIL before decomposition.
Wow. So even if a component is developed to ASIL-BD, its integration and verification testing still follows the stricter ASIL-D processes.
That's generally the principle, yes. It strongly reinforces the idea that the overall safety rigor isn't actually reduced. It's just managed more efficiently and intelligently across these proven independent elements.
Okay, this is where the strategy really shines, but it's also clearly where the devil is in the details. ASIL decomposition is, it's a sophisticated strategic tool, definitely not a loophole.
Absolutely.
It demands a really profound understanding of independence and just tons of robust evidence to back it all up. You can't just wish your ASIL-D requirement away. You absolutely have to earn the right to decompose it through meticulous engineering and rigorous analysis.
You've summed it up perfectly.
All right, so we have this ASIL framework setting the bar for safety rigor. We have ASIL decomposition as a smart way to manage that rigor. But the big question becomes, how do engineers actually find all these potential ways a system could fail in the first place?
Right. How do you identify the risks you need to mitigate?
Exactly. It feels like detective work. What are the actual tools, the methodologies for that systematic investigation?
That's precisely where safety analyses, which are rigorously detailed in Clause 8 of Part 9, come into play. These are the essential tools engineers use to ensure that the risk of a safety goal violation is sufficiently low.
And that covers different kinds of failures.
Yes, whether the violation might stem from systematic faults, things like errors in the requirements, bugs in the software logic, mistakes in the hardware design.
The human error type stuff.
Often, yes. Or it could be due to random hardware faults, like a transistor failing unpredictably due to aging, or a resistor burning out due to a manufacturing defect. These safety analyses are really the backbone of proving the safety case.
Okay, so what do these analyses actually do? What's their scope?
Their scope is incredibly broad, actually. They're used right at the beginning for validating the initial safety goals and concepts, making sure they make sense. Then, as the design evolves, they're used for verifying the detailed safety concepts and requirements against that design.
Finding mismatches.
Finding mismatches, finding gaps, yes. They systematically identify conditions and causes, including all sorts of faults and failures that could potentially lead to a safety goal or a specific safety requirement being violated.
So finding the failure pathways.
Exactly. But they go beyond just identification. They also help in defining the required responses. What should the system do when a fault is detected? How quickly does it need to react? They can even lead to defining additional safety requirements for fault detection and control if the analysis uncovers something unexpected.
So the analysis feeds back into the design.
Absolutely. It's iterative. They provide crucial evidence for the suitability of the safety concepts themselves, proof that the chosen safety mechanisms are actually effective. And ultimately, they support the identification of necessary design requirements and, really importantly, rigorous test requirements.
How do they help with testing?
Well, if an analysis identifies a specific subtle failure mode, that can directly lead to defining a new, specific safety-related test case to ensure that failure mode is either impossible or properly handled. It ensures the testing is targeted at the real risks.
So these aren't just like academic thought experiments sitting on a shelf.
Not at all.
They are the systematic investigation that underpins all functional safety. They transform those abstract safety goals into concrete, verifiable engineering actions and proof.
Got it. They are fundamental working tools. And it's important to understand the two main classifications of safety analysis methods that ISO26262 talks about.
Okay, what are they?
First, you have qualitative methods. These are primarily used to identify potential failures and their effects, but they generally don't try to predict how often those failures might occur.
So the what-if scenarios.
Exactly. They're great for mapping out possibilities. Examples include qualitative FMEA, failure mode and effects analysis, qualitative FTA, fault tree analysis, HAZELP, hazard and operability study, and ETA, event tree analysis. The standard even mentions these can be applied to software sometimes, especially if more formal software analysis methods aren't readily available.
Okay, qualitative focuses on identification. What's the other type?
The second type is quantitative methods. Now, these go a significant step further. They actually try to predict the frequency of failures, particularly for random hardware failures.
So they put numbers on the likelihood.
They do. But to do that, these methods require additional knowledge. You need quantitative failure rates for the hardware elements involved, numbers like FIT rates, failures in time, often derived from component reliability databases or testing.
And examples of quantitative methods.
Examples here include quantitative FNEA, quantitative FTA, Markov models, and reliability block diagrams. These are the tools used to calculate things like the probability of safety goal violation due to random hardware failures.
Okay, that's a key distinction. Quantitative is for predicting frequency, mainly for hardware failures.
Correct. It's crucial to remember that these quantitative methods in ISO 26262 specifically address random hardware failures, the unpredictable physical breakdown of components. They are generally not applied to systematic failures.
How are systematic failures handled then?
Systematic failures, the design errors, the software bugs are primarily addressed through having robust development processes, rigorous verification and validation activities, and strong quality management, backed up by qualitative analyses to find flaws in logic or design. You can't easily put a failure rate on a software bug.
Right. You focus on preventing them and finding them through process and review. Okay, that distinction between qualitative and quantitative is really key. One identifies the potential problems, the other predicts how often the random hardware ones might actually occur.
Precisely.
Now, let's maybe dive into some specifics. You mentioned FMEA. How does an inductive analysis like failure mode and effects analysis actually work? What does it contribute?
Okay, FMEA. Inductive analysis methods like FMEA are what we generally call bottom-up approaches.
Bottom up.
Yeah, they start from the bottom, the individual components, the sub-elements, specific functions, and they look at known or potential failure modes for those individual pieces. Then, they systematically work upwards to identify the possible effects of those individual failures on the larger system.
So starting small and seeing the ripple effect?
Exactly. It's like taking apart every single brick in a wall, examining each one and asking, okay, if this specific brick develops a crack or crumbles, what happens to the integrity of the rest of the wall? What's the end effect at the system level? It's a very meticulous, granular approach.
And you mentioned a quantitative FMEA.
Yes, focusing specifically on quantitative FMEA, or sometimes called FMETA, adding diagnostic analysis, it plays a really crucial role in verifying a hardware design against those predefined targets for hardware architectural metrics we talked about.
The SPFM and LFM.
Exactly, the single point fault metric and the latent fault metric. To recap briefly, SPFM measures how well safety mechanisms cover failures that could directly violate a safety goal on their own single point faults.
Yeah.
LFM assesses how well hidden undetected faults, latent faults are detected or controlled before they can combine with another fault to cause a problem.
So quantitative FMEA helps calculate those metrics.
It's the primary tool for it, yes. It helps quantify just how effectively the safety mechanisms are performing in the face of potential random hardware failures.
Yeah.
And by its very nature, quantitative FEA requires having those precise quantitative failure rates for the individual hardware elements. You need the failure rate data to calculate the metrics.
Makes sense.
And, as a side benefit, inductive analyses like FEA can also help support the identification of potential dependent failures.
How so?
Well, as you go through component by component, you might notice, hey, we have several identical parts here, or these different parts seem susceptible to the same type of failure mode. That can flag areas where a common cause might take out multiple elements simultaneously.
So the process itself can reveal potential dependencies.
Clever. So if a specific part could fail, FEA helps you map out that ripple effect. What happens next? What's the ultimate consequence? And maybe even how often it might occur if you're doing the quantitative version.
Exactly. It's about seeing the potential chain reaction before it ever starts and potentially quantifying the likelihood of it. Okay, that's the bottom-up view. Now, what about the other side of the coin? You mentioned deductive analysis, specifically fault tree analysis, or FTA. How does that work?
Right, FTA. Unlike FMEA, deductive analysis methods like FTA are top-down approaches.
Top-down, so starting from the big picture.
Exactly. They begin with an undesirable top-level event. This is usually the violation of a specific safety goal, like unintended acceleration occurs or complete loss of braking function. You start with the thing you absolutely want to prevent.
Okay, the disaster.
The disaster, yes. And then you systematically trace backward from that top event to identify all the potential underlying causes, all the combinations of faults, failures, or external events that could possibly lead to that critical top-level event occurring.
So working backwards from the effect to find the causes.
Precisely. You ask, for this bad thing to happen, what had to have gone wrong immediately beforehand? And then for those things, what had to happen for them to occur? And you keep tracing back until you get to basic initiating events like a specific component failure, a human error, or an environmental condition.
How is that represented?
FTA builds a graphical and logical representation of these fault pathways. It uses standard symbols, logical gates like A and D, where all inputs must occur, and OR gates, where any input is sufficient, to connect basic events up to the top-level event.
So it creates a visual map of failure logic.
A visual map, exactly. And this allows engineers to identify critical failure paths, the sequences of events most likely to lead to the hazard. It also helps identify what are called minimal cut sets.
Minimal cut sets?
Yeah, the minimal cut set is the smallest combination of basic events that, if they all occur, will guarantee the top-level event happens. Finding these highlights the key vulnerabilities, the smallest groups of simultaneous failures that could cause the disaster.
That sounds incredibly powerful for understanding complex failure interactions.
It is. The visual and logical representation is very effective. And similar to FMEA, deductive analyses like FTA are also instrumental in identifying potential dependent failures.
How does FTA help find dependencies?
Well, when you analyze the minimal cut sets, you might find the same basic event appearing in multiple cut sets leading to different top events, suggesting it's a critical common component. Or you might just visually see the same event repeated in different branches of the fault tree, clearly pointing to a potential common cause that could trigger multiple failure paths simultaneously.
It's like reverse engineering that disaster, like we said, starting with the outcome you absolutely must avoid, and then meticulously figuring out every single sequence or combination of events that could possibly lead you there. It sounds exhaustive.
It is exhaustive, yes,
Yeah.
but absolutely necessary for complex systems. And that's precisely why the standard emphasizes the complementary power of using both approaches, inductive and deductive.
They work together.
Absolutely. Inductive analyses like FMEA and deductive analyses like FTA are not mutually exclusive. They are profoundly complementary. By applying both methods, you significantly increase the coverage and the robustness of the overall safety analysis. You get a much more comprehensive understanding of the potential failure scenarios.
Because they look at the problem from different directions.
Exactly. One looks from the individual parts upward, asking, what happens if this fails? The other looks from the system-level failure downward, asking, what could have caused this? Together, they provide a much fuller, more reliable picture of a system's safety vulnerabilities and strengths.
It really is a belt and suspenders approach then, making sure no stone is left unturned in the hunt for potential safety issues, whether you're starting from the component level or from the worst-case system event.
That's a perfect description. It provides multiple reinforcing layers of assurance that you thoroughly analyze the risks.
Okay, we keep circling back to this idea of sufficient independence, especially when we talked about ASIL decomposition. It really feels like a foundational requirement for making these advanced safety strategies work.
It absolutely is.
But let's get into the weeds now. What exactly are dependent failures? Why are they considered such a significant, maybe even insidious threat to safety if they're not properly understood and managed?
Right. This brings us squarely to Clause 7 of Part 9, which is dedicated to the analysis of dependent failures, or DFA. This is a truly crucial aspect of functional safety engineering.
Okay, DFA. What are its main goals?
Its core objectives are really twofold. First, it's about rigorously confirming that a required level of independence, or sometimes called freedom from interference, has actually been sufficiently achieved in the system's design.
So proving the independence we talked about earlier.
Proving it, yes. And second, if the analysis does identify plausible dependent failures, the DFA aims to define the necessary safety measures to mitigate them effectively. It's about making absolutely sure that your carefully designed safeguards don't secretly undermine each other, or that some single hidden flaw doesn't compromise multiple layers of your safety protection simultaneously.
Undermining safeguards. How can that happen? What types of dependent failures are we talking about?
The standard identifies two primary types of dependent failures that directly threaten the crucial independence needed for things like ASIL decomposition. The first type is perhaps more intuitive: cascading failures.
Like dominoes.
Exactly like dominoes. These occur when the failure of one element directly causes or significantly exacerbates the failure of another element downstream. The standard gives a clear example we touched on earlier. Erroneous vehicle speed information transmitted to other vehicle functions, and thus affecting their behavior, is a cascading failure.
Right, but bad sensor reading messing up other systems that rely on it.
Precisely. A problem in the speed sensor could cascade, leading to malfunctions in adaptive cruise control, stability control, automatic braking systems, creating a dangerous chain reaction from a single initial fault.
Okay, that makes sense. What's the second type?
The second type, and this is often the more subtle and, frankly, more insidious one, is common cause failures, CCF.
Common cause, meaning...
These are failures where a single underlying event, or perhaps a shared design flaw, leads to the simultaneous or near simultaneous failure of multiple, seemingly independent safety functions or elements.
Seemingly independent.
Yes, that's the insidious part.
Yeah.
You might have designed beautiful redundancy, two separate systems doing the same critical function. But if they both share a common vulnerability...
Like what?
Like, maybe they're both powered by the same single, potentially fragile component. Or maybe they're both located close together and susceptible to the same environmental stress, like extreme heat or vibration. Or perhaps they use the same flawed software library. If that single event or flaw occurs, it could take out both of your redundant systems at the same time, completely defeating the purpose of the redundancy.
Wow, that sounds much harder to spot.
It can be. The standard gives some powerful examples here, too. One is a high-intensity electromagnetic field that causes different electronic devices to fail in a way that depends on design and use is a common cause failure. Imagine a sudden strong burst of electromagnetic interference, maybe from an external source that simultaneously disrupts or damages multiple electronic control units that were supposed to be independent backups for each other.
Okay, an external shock hitting multiple things.
Right. Another, even more subtle example they give is A monitor designed to detect anomalous behavior of a function can be rendered inoperative sometime before the monitored function fails if both the monitor and the monitored function are subjected to the same event or cause.
Wait, so the safety monitor fails with the thing it's monitoring?
Which is a common cause failure, yes. Imagine the monitor and the main function both rely on the same power source, or the same timing crystal, or are both susceptible to the same software bug. The very safety mechanism designed to protect you fails alongside the primary function due to some shared weakness you might not have initially anticipated.
Yikes. Okay, so it's definitely not enough just to make sure individual parts are robust on their own.
Not at all.
You absolutely have to ensure that a problem in one part doesn't bring down a whole chain of others, the cascading failures. And, maybe even more subtly, you have to hunt for those single hidden flaws or shared vulnerabilities that could silently undermine multiple safeguards all at once, the common cause failures.
That's it exactly. It's about understanding this systemic vulnerability, hunting for those hidden interconnections that might seem harmless individually, but could collectively lead to catastrophic consequences.
And you mentioned this concept of independence is critical elsewhere, too.
Yes, it's incredibly critical because it underpins multiple fundamental aspects of functional safety design, according to ISO26262. It's not only the key enabler for ASIL decomposition, which we spend time on,
Right.
but it's also absolutely crucial for justifying the coexistence of elements with different ASILs, or even safety-related elements coexisting with non-safety-related elements within the very same physical component, like on the same circuit board or inside the same electronic control unit, ECU.
Mixing different levels of criticality on one chip or board.
Exactly. This coexistence relies heavily on demonstrating what the standard calls freedom from interference.
Freedom from interference. How is that different from just independence?
It's closely related, but freedom from interference specifically means demonstrating with rigorous evidence that a non-safety-related sub-element, or maybe a sub-element developed to a lower ASIL, cannot either directly or indirectly violate any safety requirement allocated to a higher ASIL sub-element that it shares resources within the same component.
So, making sure the less critical stuff can't mess up the more critical stuff they live with.
Precisely. This concept is all about preventing cascading failures within a shared element or component. You need to prove, for example, that the non-safety critical software partition won't accidentally overwrite the memory used by the safety critical partition, or that it won't consume so much processing power that the safety function gets starved and can't react in time.
Okay, so it's about partitioning and protecting resources within a shared environment.
Exactly. And to help engineers systematically find all these potential dependent failures, both common cause and cascading the standard, provides really helpful guidance. Annex C offers a framework for identifying dependent failures, which includes practical coupling factor classes.
Coupling factor classes, like categories of potential problem.
Basically, yes. They are essentially detailed checklists or categories of potential interdependencies that engineers should investigate. They use these as a guide to improve the completeness and rigor of their DFA, making sure they don't overlook subtle ways elements might be linked.
Can you give some examples of these coupling factors?
Sure. Let's look at a few key categories that really illustrate the kinds of hidden connections you need to look for. One critical area is shared resource.
Okay, like sharing hardware.
Exactly. This occurs when the same software library, the same hardware component, maybe the same communication bus, or even the same system instance is used by multiple elements. This makes them all vulnerable if that shared resource fails, gets corrupted, or becomes unavailable.
Examples.
Imagine a common power supply that feeds both the primary braking controller and its redundant backup controller. If that single power supply fails, both controllers go down simultaneously, completely defeating the redundancy. Or think about a shared software component, like a mathematical library used by both a safety function and a non-safety function. A bug in that shared library could affect both. Or even a single H-bridge driver chip that's physically used by two separate shutdown paths, a failure in that shared chip would compromise both safety paths.
Okay, shared physical or logical things are a big one. What else?
Another important coupling factor is insufficient environmental immunity. This refers to situations where elements, even if functionally independent, has similar physical characteristics that make them susceptible to the same external environmental disturbance.
Like the electromagnetic interference example.
Exactly. If two seemingly independent sensor circuits are housed close together in the same module, and both are highly sensitive to EMI, a strong EMI burst could potentially knock out both at the same time. Or think about a shared housing that's vulnerable to water ingress. If water gets in, it could cause multiple internal components to fail simultaneously due to short circuits, even if they were functionally separate.
So shared vulnerability to the outside world.
Right. Then there's unintended interface. This is perhaps one of the trickiest categories to identify comprehensively. This is when two elements affect each other directly, but via an interaction that was not anticipated or designed.
How could that happen?
It could be something like one software functionality accidentally overruling another because their timing wasn't properly synchronized, or maybe an issue where two processes share memory space, and one causes memory allocation conflicts or memory leaks that eventually starve or crash the other process. These are the subtle, often overlooked runtime interactions that can create critical vulnerabilities.
Those sound really hard to find just by looking at schematics.
They are. They often require deep analysis of the software architecture and behavior. The standard provides many more examples of these coupling factors, things like shared information inputs, systematic coupling due to common tools or processes using identical component types, communication channel failures, all designed to guide engineers in their forensic analysis of potential hidden dependencies.
Wow. Okay, these coupling factors really are the specific, often quite subtle ways that vulnerabilities can creep into a system. It's all about looking for those hidden connections, those shared resources or weaknesses that might seem harmless in isolation, but could become critical failure points under the right circumstances. Almost like finding invisible tripwires in the design.
That's a great analogy. Invisible tripwires.
So what happens once these potential dependent failures, these tripwires, are identified using these methods and checklists? How are they actually mitigated or dealt with in practice? And what are some of the challenges in doing that effectively?
Right. Once potential dependent failures are identified, the next crucial step is that they must be rigorously evaluated for plausibility.
Plausibility, meaning could it actually happen?
Exactly. It involves determining if a reasonably foreseeable cause exists that could realistically lead to that specific dependent failure scenario occurring, and subsequently violating the required independence or freedom from interference. This evaluation isn't just a quick check. It has to consider all the relevant operational situations, different vehicle operating modes, and environmental conditions.
Is it possible to quantify the probability of these dependent failures?
That's a major challenge. The standard actually clarifies that quantifying the probability of common cause failures and cascading failures is generally estimated only on a qualitative basis. There isn't currently a universally accepted reliable method for precisely quantifying the probabilities of these complex, often subtle interactions. So the focus is more on identifying plausible scenarios and ensuring robust mitigation rather than calculating an exact probability number.
Okay, so if plausible dependent failures are found, what then?
If plausible dependent failures are indeed identified, then specific measures for their resolution must be defined and implemented during the development phase. You can't just identify them and leave them.
What kind of measures?
These measures generally aim to do one of three things. Either prevent the root causes of the dependency from occurring in the first place, control the effects if the failure does occur, perhaps by detecting it quickly and transitioning to a safe state, or reduce the coupling factors themselves, breaking the hidden connection.
Can you give an example of a mitigation measure?
A very common and powerful measure, especially against common cause failures, is introducing diversity.
Diversity, like using different parts.
Yes. It means intentionally using different technologies, different design approaches, components from different suppliers, or even different software algorithms or programming languages for redundant elements that perform the same safety function.
How does that help?
Well, if two independent systems doing the same job are designed by completely different teams, using different programming languages, running on different types of microcontrollers, maybe even using different sensing technologies, it becomes far, far less likely that a single systematic design flaw or a single type of environmental stress could affect both of them simultaneously. Diversity breaks the commonality.
Makes sense. Deliberately making them different makes them less likely to fail together from the same cause.
Precisely. And finally, the standard stresses that the rigor of this entire dependent failure analysis must be appropriate for the risk involved.
Meaning?
The DFA has to be performed with a level of detail and thoroughness suitable to effectively demonstrate that the required independence or freedom from interference has genuinely been achieved. How much rigor is needed depends on factors like the ASIL level of the safety goal being protected, the overall complexity of the product, the specific technologies involved, and any potentially adverse environmental factors the vehicle might realistically encounter throughout its operational life.
So higher ASIL, more complex system, harsher environment means a more intense DFA.
Absolutely. And one of the biggest ongoing challenges here, frankly, is proving the absence of a potential fault or a harmful interaction. Proving a negative is inherently difficult. Engineers are constantly pushing the boundaries of analysis tools, simulation methods, and verification techniques to get better and better at achieving this deep level of assurance.
So it really is a constant deep dive into anticipating every conceivable way a system could fail due to these hidden connections, and then proactively building in safeguards like diversity or partitioning to prevent or mitigate those failures. It's about designing for resilience against unexpected interactions, not just designing for the intended functionality.
Exactly. Making sure that one single weak link, perhaps a shared resource or a common vulnerability, doesn't bring the whole safety chain crashing down. It's like building that fortress, but then also meticulously searching every inch for any secret tunnels, shared foundations, or common weaknesses that an attacker, or in this case a failure event, could exploit.
Okay, this has been an incredibly detailed look at these different layers of analysis. We've covered how ASILs set the fundamental bar for safety rigor, how ASIL decomposition provides a strategy to manage that complexity.
Right, under strict conditions.
Under strict conditions, yes. And then how specific safety analysis methods like FMEA, bottom-up, and FTA, top-down, are used as the detective tools to find potential failures.
Complementary tools.
Complementary tools, absolutely.
Yeah.
And finally, the critical vigilance required for dependent failure analysis, hunting down those cascading and common cause failures. It really sounds like these analyses aren't just a one-time check done at the end.
Oh, absolutely not.
They seem deeply integrated into the entire development process, right? How do they actually fit into the bigger picture of a vehicle's overall functional safety lifecycle?
You've hit on a really crucial point that sometimes gets overlooked when people first learn about these methods. ASIL decomposition, dependent failures analysis, and the general safety analyses like FMEA and FTA. They are emphatically not isolated activities. They're not one-off checklist items you perform at a single point in time and then forget about.
So they're ongoing.
They are continuous, iterative processes. They are applied repeatedly throughout the entire functional safety life cycle of an item, meaning the system or component being developed. This starts right from the earliest initial concept phase, continues all the way through detailed product development at the system level, then drills down into the hardware level, and finally the software level.
And they change as the design evolves.
Exactly. These analyses are performed at appropriate levels of abstraction. Early on in the concept phase, you might be doing high-level hazard analyses to define the initial ASILs and safety goals.
Yeah.
As you move into the system design phase, you'll likely perform initial ASIL decomposition studies and high-level safety analyses, maybe a system-level FMEA or FTA, to define and refine the functional safety concept, the overall strategy for achieving safety.
And then later.
Then, as you get down to the detailed hardware and software design levels, you conduct much more detailed FMEAs, or FMETAs for hardware metrics, detailed FTAs, and that rigorous dependent failure analysis we just discussed. These are used to verify the technical safety requirements and the specific architectural design choices made for the hardware and software components.
So the level of detail increases as the design gets more concrete.
Precisely. Each phase builds upon the analyses and outputs of the previous one. It's a continuous process of refining the safety case, identifying potential issues introduced by detailed design decisions, and proving that the safety measures are effective as the design matures. These activities are absolutely integral to the well-known V-model development process often used in automotive, where safety requirements are defined down one side of the V, and verification and validation activities, including these analyses, happen at each corresponding level on the way up the other side.
Right. So they're like these constant vigilant guardians, aren't they? Continually assessing, refining, and adapting the design at every single stage of a vehicle's journey, from just an idea on paper to the actual reality driving on the road. It ensures safety is truly baked in from the very beginning.
Exactly.
Not just bolted on as an afterthought or treated like a final checkbox exercise before launch.
That's a perfect way to put it, baked in, not bolted on. And the overarching importance of performing these analyses thoroughly and iteratively for functional safety really cannot be overstated.
Why are they so fundamentally important, in summary?
Well, first, they are fundamental for identifying hazards. Not just the hazards you already knew about from past experience, but potentially new or previously unknown hazards that might emerge as the design evolves, or especially as new complex technologies like automated driving features are integrated.
Finding the unknowns.
Finding the unknowns, yes. And they are crucial for pinpointing the specific faults, the specific failures, the specific conditions that could actually lead to the violation of those top-level safety goals or the derived safety requirements. It's about being proactive, not reactive, when it comes to potential danger.
Okay, identification is key. What else?
Beyond just identification, these analyses provide the solid, indisputable basis for defining effective safety measures. And that includes the whole spectrum. Strategies for fault prevention, stopping issues before they even start, through robust design rules, coding standards, careful component selection, fault detection, catching problems if they do occur, through clever diagnostics, monitors, plausibility checks, and strategies for effect mitigation, minimizing the harm if a fault manages to progress, through things like transitioning to a safe state, graceful degradation of performance, or warning the driver.
So they don't just find the problems, they rigorously guide the development of the solutions too.
Exactly. They drive the safety architecture. And third, they offer powerful, tangible evidence. They provide the proof needed to demonstrate the suitability and the actual robustness of the safety concepts that have been designed into the vehicle. It's the objective evidence that shows the intellectual work of designing for safety actually translates into a demonstrably safer product.
The proof in the pudding.
The proof in the pudding.
Ah.
Furthermore, they actively support the verification of those safety concepts and safety requirements throughout development. And as we mentioned, they critically guide the identification of necessary design constraints and, very importantly, the critical test cases needed for validation.
Right, feeding the testing strategy.
Yes. In fact, if new fault models or unexpected failure modes are identified during these analyses late in the process, they can and should lead to the definition of entirely new safety-related test cases, ensuring that the testing strategy evolves dynamically with the engineer's understanding of the potential risks.
So it's a closed loop, feeding back information constantly.
Ideally, yes. And ultimately, when you put it all together, these comprehensive analyses, the ASIL determination, the decomposition justification, the FEAs, the FTAs, the DFA, they collectively provide the strong foundation and the rigorous evidence required to demonstrate that the residual risk of a safety goal violation is sufficiently low, meeting the criteria set by the standard and societal expectations.
And that's the bottom line for release.
That rigorous, evidence-based approach is exactly what allows engineers and manufacturers to formally justify the safety acceptance of the vehicle's complex electrical and electronic systems. It provides the ultimate assurance, backed by documented proof, that the vehicle is safe for its intended use on public roads. It's really a testament to the incredible dedication to safety that drives the entire automotive industry.
It really is. Which I think raises an important question, maybe for you, the listener, to think about. When you get into a modern vehicle, you don't consciously think about ASIL-D decomposition or quantitative FMEA or dependent failure analysis. Of course not.
No, you just want to get where you're going safely.
Exactly. But understanding this now, understanding these meticulous, often completely unseen layers of analysis that go into every single safety-related aspect of that vehicle, how does knowing about this deep engineering rigor fundamentally shape your trust and your experience next time you turn the key or engage a safety feature like cruise control or lane assist? What maybe stands out to you as the most surprising or impactful insight from our deep dive today?
It's been quite a journey, hasn't it? We've taken a really comprehensive tour through the core of ISO26262-Part 9, uncovering some of the most critical analytical aspects of automotive functional safety.
We really covered a lot of ground.
We did.
Correct.
We started by understanding ASIL, the Automotive Safety Integrity Level, as that fundamental driving force of safety rigor, dictating the strictness required for every phase of a vehicle's life based on risk.
The North Star.
The North Star, exactly. We then delved into the strategic advantages, but also the very strict conditions of ASIL decomposition, learning how those demanding high ASIL requirements can be intelligently managed across proven independent elements, but only if that independence is rigorously demonstrated.
No shortcuts there.
No shortcuts. Our detective work then led us through the essential safety analysis methods. We distinguished between the bottom-up, inductive approaches like FMEA and FMETA, which map component failures upwards to their system effects,
right,
and the top-down, deductive approaches like FTA, which trace catastrophic events downwards to find their root causes. And we really emphasize their complementary power in uncovering every potential weakness.
Belt and suspenders.
Belt and suspenders indeed. And finally, we explored the critical vigilance required against dependent failures, being constantly on the lookout for both those direct cascading effects and those insidious common cause vulnerabilities, understanding how a single underlying flaw or shared resource could silently undermine multiple layers of safety protection if not found to mitigate.
That's right. And listening to all this, it really reinforces that this isn't just about abstract technical standards or complex diagrams filled with acronyms.
No, it's very practical.
It's about the invisible, meticulous, sometimes painstaking engineering effort that creates the confidence and the trust we instinctively place in our road vehicles every single day. The next time you're driving, maybe just take a brief moment to appreciate the thousands upon thousands of hours of detailed analysis, simulation, verification, and thoughtful design that went into making that simple act of driving a safe one for you, your passengers, and everyone else sharing the road.
It's a really good point. Consider how these incredibly complex layers of analysis, all rigorously applied, constantly reviewed, and continually evolving with technology, are precisely what make the seemingly simple act of driving a profoundly safe one, statistically speaking. And maybe looking ahead, here's a thought to ponder. What might be the next frontier improving and ensuring this essential level of functional safety, especially as vehicles become even more autonomous, vastly more interconnected through networks, and even more deeply integrated into the fabric of our smart cities and our daily lives? How will these analyses need to evolve to meet the challenges of that future, transforming our relationship with transportation itself?